Suppose Alice wants to send information to Bob, and we know that if Alice uses qubits and send it through a quantum communication channel, she can at least communicate 1 bit of classical information per qubit. This can simply be done by Alice prepare her qubit in either state 0 or state 1, and the 0 and 1s represent the bit of information she wants to send. On Bob's side, Bob just needs to do the measurement in exactly the same basis, which is the computational basis. If Bob finds his state in 0 state, the information he concludes must be 0, which is the same as the information Alice wants to send. Otherwise, he will say the information is 1, which is also correct. So we conclude that it is no worse off using a quantum communication channel and qubits than using a classical communication channel. But can the quantum communication do better than classical communication? Can Alice probably send more information to Bob per qubit that is transmitted through the communication channel? The answer is yes, and for that, we need entanglement. Here, this is a simple protocol that shows quantum advantage in communication. Let's see how it works. Suppose Alice and Bob share this pool of entangled state in this way. This is the Bell state psi plus in the form of 0, 0 plus 1, 1. And one of the qubit is with Alice, the other qubit is with Bob. For convention, we call Alice qubit qubit 1 and Bob's qubit qubit 2. It does not matter when this entangled 2-qubit system is prepared and who prepares it. It also does not matter how far Alice and Bob are physically separated. What it matters is that at the time when Alice wants to communicate with Bob, they have this perfectly shared entanglement in this Bell state that Alice can use directly. The claim now is that by just sending one physical qubit to Bob, Alice can send 2 bits of classical information, that is 0, 0, 0, 1, 1, 0, or 1, 1 to Bob simultaneously. Let's see how she can actually do that. If she wants to send over the information 0, 0, she does nothing on her qubit and directly send it over to Bob. Now Bob is in possession of both qubits, and the 2-qubit system is in state phi plus. If Alice wants to send over the information 0, 1, she would do an X operation on her qubit before sending it over to Bob. And this on the 2-qubit system would be the operation X tensor I, where the identity is the action on Bob's qubit. And this now acts on our Bell state. The X operation flips 0 and 1 around, so we will now have 1 over square root 2, and this 0 becomes 1, this 1 becomes 0, so this gives 1, 0 plus 0, 1 state, which is another Bell state denoted by psi plus. Okay, so now Bob would receive a psi plus state on his side. If Alice wants to send the information 1, 0, he will then do a Z operation on her qubit before sending it over to Bob, and the Z operation does not change the 0 state, but it adds on the minus phase to the 1 state. So this acts on the phi plus state would give 1 over square root 2. It does nothing to the first term, but gives a minus sign to the second term. So we get 0, 0 minus 1, 1. This is another Bell state That was the phi minus state. Finally, if Alice wants to send over information 1, 1, she will now do the IY operation. This is the imaginary number I times the poly Y operation. So let's see how it transforms the states. The IY operation changed the state 0 to -1 and changed the state 1 to 0. So X on the bound state that we have, this would becomes minus 1, 0 plus 0, 1, which is exactly the other bound state that we have, denoted by psi minus. So again, now, when Alice wants to send 1, 0, Bob would receive the state phi minus. When Alice wants to send 1, 1, Bob would receive psi minus. We have seen previously that these 4 bound states also form an orthonormal basis for the 2-qubit system. So if Bob can do 2-qubit measurement and project the qubit that he has into this basis, he can perfectly decode the information that Alice sent to him by saying that when he finds the state is phi plus, he will say that Alice sent 0, 0. When he finds the state is psi plus, he will say Alice sent 0, 1, so on and so forth. So the 2 bits of information Alice wants to send to Bob can be perfectly decoded if Bob can do a projective measurement in this basis. However, such 2-qubit joint measurement is normally difficult to implement. What Bob can normally do in his lab is do single qubit measurement. That is, he can measure the first qubit and then measure the second qubit, or sometimes measure the 2 qubits simultaneously, but not a joint measurement on both qubits. So we would also see next that if Bob can only do single qubit measurement, he can also perfectly decode the information Alice wants to send to him. If Bob can only do single qubit measurement, he can also decode the information, but before he does that, he will need to do a CNOT operation on the 2-qubit system, followed by a Hadamard operation on the first qubit. Let's see how this operator acts on the state Bob has. The CNOT operator, also called the control NOT operator, is the operation flips the second qubit if the first qubit is in state 1. So it can be denoted by the matrix 1, 1 and 0, 1, 1, 0. Well, the Hadamard operation, it transforms basis 0, 1 into the plus minus basis. And vice versa, it also transforms the plus minus basis into the 0, 1 basis because it is a Hermitian operation. It's in the form of 1 over square root 2, 1, 1, 1, minus 1. So if we have the state phi plus, for example, and now by first applying the CNOT gate, this is 1 over square root 2, 0, 0 plus 1, 1. The CNOT operation does nothing to this because the first qubit is 0, but it flips this bit around, flips the second qubit from 1 to 0 because the first qubit is in 1. So this would change the state into 1 over square root 2, 0, 0 plus 1, 0, which we can rewrite it as 1 over square root 2. A state on the first qubit, 0 plus 1, tensored with 0 on the second qubit. This, we immediately recognize this as the plus state. So now, by applying the Hardeman operation on the first qubit, it will change the plus state into a 0 state. We will end up with a 0, 0 state. So by doing this operation, it transforms the phi plus state into the 0, 0 state. One can also verify that by following the same procedure, it transforms the psi plus state into 0, 1, the phi minus state into 1, 0, and the psi minus state into 1, 1. So now Bob just needs to do projective measurements in the computational basis instead to find out what is the information Alice sent to him by projecting into the computational basis, which is a tensor product basis. In summary, we have now seen that by just sending one qubit to Bob, Alice can communicate 2 bits of classical information, making use of the pre-established entanglement between them. This is known as dense coding or the super dense coding. This protocol also offers additional security because now, if an eavesdropper wants to intersect the state Alice sent to Bob, he or she will not get any information by just measuring that particular state. Because information is not encoded in any one of the qubits, but in the shared entanglement. In this sense, entanglement is used as a resource here. Nevertheless, there are still 2 qubits involved in this communication channel because measurement on one single qubit can maximally offer 1 classical bit of information. So for Bob to gain 2 bits of information, he needs to at least measure 2 qubits. However, only 1 qubit is transmitted at a time when communication is needed. This wouldn't be possible in the classical world.